Okay, thank you very much for this wonderful evening. I'm going to talk a bit about what we're doing from Polis's side, and especially we're going to talk. I'm going to stand over here, so I'm not walking. Yeah, so I'm going to talk mostly about the work that we've been doing on for the Parquet reader. So my name is Gijs. I've been working at Polis for a bit more than 1.5 years now. I work on kind of everything, but one of the main things that I've done over the 1.5 years is I've worked a lot on speeding up the Parquet reader. So I kind of first want to talk a bit about this title. So for the people that don't know, Parquet is a format that is used a lot in the data science world, basically to store any kind of columnar data. It's used everywhere from Iceberg to Data Lake, and even to like host databases. There's companies that use Parquet for that. Parquet is heavily made to be vectorized, so you can scan it very quickly, you can decode it very quickly, you can seek very quickly. And since this is the main source that people really use for data science nowadays, maybe together with CSV, we spend a lot of time making it actually fast. And specifically, we looked a lot more into what a lot of other companies looked a little bit less, which is doing predicate pushdown in a vectorized way. So maybe first, why do we care, right? So we look a lot at benchmarks because we're trying to speed up polars, and we have this benchmark, which is the PDSH benchmark, which is one of the main benchmarks that we use. And when you actually look at what it's spending its time on, at least on my computer, and I think on a lot of other computers as well, it's spending a lot of its time just reading Parquet. And this depends very much on what query you're looking at and what it's kind of doing. You can see here there's one query that's literally spending 99% of its time scanning Parquet. So you can see that if you don't optimize this side, you can never really get that much faster. And we already optimized completely we already optimized way too much on this side, so we should really spend some time optimizing this side, right? So I want to talk firstly a bit about like what generally happens when you try to optimize I/O and specifically Parquet, and then I want to talk about two things that Polis has specifically done to optimize for this. So I want to start a bit with this row group statistic, which is one of the most well-known things that Parquet allows you to do, right? So when you look at scanning I/O efficiently in a columnar format, there's two main things you're looking for. So there's predicate pushdown, which is what rows do we actually want from our file, and then there's projection pushdown, and that means what columns do we actually want from our file, right? So since Parquet is a columnar format, you actually get this projection pushdown for free. Since your data is standing contiguously in your file, you can just choose to skip parts of your file, and then you don't need to actually look at it, and it's very simple. This predicate pushdown side is much harder, and that's what we will be spending the rest of the night talking about. Because two reasons. First of all, your data is not contiguous in memory. The data that you're looking for will not be contiguously in memory. That is true for stuff like CSV or there's Avro as well, which has this as well, where your rows are contiguous in memory. But there's also another dimension which is hard, which is that predicates can get arbitrarily complex, right? You can literally have semi-joins or whatever kind of weird predicates you might have, where your expression is just completely crazy. So in Parquet is split up kind of hierarchically, where you have row groups, which are fixed amounts of rows for every column. And then you have some, within each row group, you have column chunks, which is this contiguous piece of data for one column. And then within that column chunk, you have many data pages with optionally a dictionary page that data pages can reference into, saying like, oh, I want value 5 out of my dictionary, or I want value 1 out of my dictionary, which allows you to do a lot of deduplication if you have some low cardinality data. And then one thing that's also very important is you have this big chunk of metadata at the end, which basically allows you to say, which contains stuff like the minimum value in this column chunk is 5, and the maximum value is 10. And then using your predicate, you can do stuff like this, where, okay, let's say the minimum was like 5 and the maximum was 10. Well, we know that our predicate is age is bigger than 17. Well, we create a new expression that says, okay, we can skip this row group if the maximum of the age is less than or equal to 17. And then we basically create a mask of all our row groups, and we say, okay, we can skip this one, we can't skip this one. And it basically allows you to just black out entire chunks of your file and just say we don't even have to look at it, which again gives you a bit of this advantage that the projection pushdown gave you, right? So these expressions can actually get arbitrarily complex again, and for some expressions you can't really do stuff on min and max statistics, but these expressions can just be combined as like, oh, I want equal, like I want everything equal to 42, and I want the price less than 100. Well, this just translates into a different expression again that you can evaluate, and again get this skip mask to skip row groups. So, having seen these, let's descend a bit more into the depth of optimizing Parquet filtering. So, the basic process then becomes, right, you have your file, you have selected your columns that you want to actually have a look at, you extract those columns with your projection pushdown, and then you do your predicate pushdown afterwards on your columns. But you might already see that this is a bit inefficient, because if let's say your predicate is again age bigger than 17, well, you just extracted the entirety of index, even though you could have beforehand just took age, see where it's true, and then just extract stuff from the index column where the age was bigger than 17. Basically, you're doing a lot of extra work for this index column, which first of all will just take longer. Second of all, it will your CPU will be busy with stuff that while it could be doing other stuff. And third of all, it will use a lot more memory, right? So what we can do instead is we can just load the columns that we need for the predicate. Then we evaluate our predicate, and then we just load the stuff from the index column that we need, right? So this is basically done like this. Like you have some, I want to decode. Okay, we have some mask. If you selected it, decode 1, add it to the buffer. Otherwise, we skip 1. And if you look in some Parquet implementations, this is almost literally what it is. And if you think about Parquet being a very vectorization-friendly Parquet format, this is kind of insane, because this is super branchy. It is super, like, you have to keep state in your data. It's completely not vectorized. This is very slow, right? So we at Polars already spent a lot of time just optimizing our filter kernel. Like, you have some data and you want to filter something out of it. We have spent a lot of time making that branchless, making that vectorized, and distinguishing between different kind of selectivities. And what we found is that doing this is actually slower in a lot of cases, because our filter is much better than doing this kind of stupid loop, right? So we were thinking, we have done all this research, can't we like do something with this in Parquet and still get the same kind of benefits? And this is basically what we did, right? So we took this thing, we did all the same research that or applied all the same research that we did for the normal, and we got quite a good reduction. And for some people that like this seems like 20% seems like nothing, but you have to realize that this is like crazy optimized already, and we're going to something else crazy optimized. So a 20% reduction of like realistic benchmarks, not just doing like some micro benchmark, is actually really, really, really like a good save. So let's step one more step deeper. If you looked at the previous thing, there's actually one more problem here, right? We're still scanning the entirety of this H column, then deciding where is our predicate true, and then we do the nice thing for the other columns. But if you have something that is very selective, you don't need to load everything from the H column. Like you just want a tiny part of your H column. So what we want to do is we want to apply two extra principles. So first we're going to take our predicate and we're going to actually split it into tiny little column predicates where we kind of ignore the name. We just want to know, okay, what are we doing here? And then the second thing is having a predicate column doesn't necessarily mean that you also want to load it into memory. Like you might have some column that you only want to filter by, but you don't actually use the value of afterwards anymore, right? So what we're going to do is we're going to have this strategy where instead of loading the whole data into memory first, we are going to evaluate the predicate on actually like the raw encoded Parquet data, which will be a bit complex, but it might save us a lot, right? Then we get a mask out of it, and then we're going to reuse our existing kernels that we wrote for this pre-filtering pass, and we have hopefully a very optimized thing, right? So there's some very nice effects of this, right? So first, if you have some dictionary encoding, you only have to evaluate your things on the dictionary, which might be a very small set, and then you can do just to use that as a lookup table for your predicates. And secondly, if you have no matches in your dictionary, well, you know that none of the rest of the data matters, right? So you can just skip that whole row group, which allows you to be even faster. And then we're going to do some specialization for some very common predicates, right? So equality, well, if you are asking whether whether in your predicate whether something is equal to something else, you can basically just do, okay, is this equal? Okay, then at the end we just set this value 20 times, and it's like much faster than again reading from the file. And then for is-in predicates, so this is basically what a semi-join would be. We can also do a similar thing to the dictionary encoding. We can make like a lookup table for all the values, and we also have something very nice, which is like basically free string duplication. And we're still planning in the future to do some other stuff that we also think will lead to like a lot of extra benefits. I'm going to skip these two for a bit, but there's a lot of benefits to doing this, right? And again, this does lead to quite a bit of reduction, and you can write micro benchmarks again that basically lead to this being like 1,000,000 times improvement. But yeah, like for realistic use cases, again, this is like a 14-15% improvement, which I think is very good. And again, you really reduce memory consumption, which is also really important, right? So, having said all of this, the question is maybe, why are some other Parquet implementations not doing this, and why did we do this, right? So, there is actually a high complexity cost to doing this, right? So you can spend all this time writing decode kernels for like your specialized predicates and all your encodings, and you will get kind of the amount of kernels that you have to write will be like the product of these two, which is tough, and it's like you have to balance for every kernel that you write. Okay, is this worth it? It's also hard to get right. Like we had some bugs in the kernels. And then when you have bugs, they are hard to debug because they're only for one specific encoding and they're only for one specific predicate. So it's also hard to like reduce and reproduce for certain users. But when you have them right, they are very fast, right? So why did we do it anyway? So POTUS is already crazy fast computationally, as we saw. So we really need to shrink this piece of the like the pie here. And I/O and Parquet is really the bottleneck for us. So I think for us it makes a lot of sense doing these kind of more straining optimizations. And I think one of the things that it's not captured that well in these benchmarks, but the memory consumption really went down by a lot. And especially if you have very selective predicates, the memory consumption becomes proportional to not the size of your file, but becomes proportional to how much you're actually selecting, which can be an arbitrary reduction in memory performance. And we have a lot of room for future optimizations that you can only do if you have done this. So it allows for dynamic filter push down, as I already said, we have these inequality predicates and these contain predicates, and these string predicates especially are very interesting because string copying is very expensive, because basically every individual string will require another mem copy again, which is very expensive. So, given that, that's kind of my talk. Please, we're hiring. Please, we have a lot of open positions. If you're interested, look us up online and you can find us there. And then I want to also leave some room for questions. I think I have enough time, so yeah, should be fine. Yes.
Have you tried the optimizations with the Parquet spec 2, so Parquet 2.0, or just with, I assume it's Parquet 1 spec?
So 2.0 is actually like, there's two 2.0s here, right?
Yeah,
so you have the data page 2.0 and you have the like the actual Parquet spec 2.0. The data page 2.0 I think is quite a big win because you can mark certain pages not to be compressible, which I think is quite a big win. I am not 100% sure about the Parquet 2.0 spec. There's a lot of encodings there that are very interesting, but we haven't written the decode kernels for those yet. Like this, like we have some general fallback that will do stuff, but the specialized stuff we haven't written.
Question for this optimization, it was also meant for data dumping directly to Parquet. So like I would say very fast and intensive write, like sensor wise.
So the writing Parquet is a bit of a different story, right? Writing Parquet can be very slow because of the encoding, actually. So if you like the specific, I don't know what your specific question is, but like for like writing Parquet is like a very different story. We do like some optimizations for this writing, but especially if you're doing like data dumping and then just loading your whole file again, this does not really apply that much because you don't really have a predicate usually, right? So I think there's also like there's a lot of people who use Parquet as well as like this temporary storage thing, and for that this does not really help that much because and actually like you're going to be way like kind of maxed out on like how optimized you are because Parquet is really fast in that sense. But for like predicates, you don't like this. That would not apply. Yeah.
In your optimization, do you always request blocks of the same size, or does this kind of selectivity allow you to request smaller chunks?
Yeah. So there's actually so you have this here, right? So there's actually quite a lot of stuff that happens here. So you have kind of like a dynamic filtering here, right? So what will happen is if you have a very high selectivity in a certain place, you will switch to a certain mode that is very well optimized for high selectivity. And then if you come to a place again where you have very low selectivity, so you're selecting a very little amount of elements, you move to a way where, more of a method where you are very optimized for that kind of filtering. And for a lot of for some of the encodings, it's actually very efficient to skip complete like parts of your encoding, and we do that as well. Like we make sure that we do that as well. But for other encodings, it's not that efficient because you can't seek that at all. Yeah.
How do you write tests for something like this?
So we write a lot of parametric tests on the kernels itself.
Yeah.
But somehow people always find strange things to do that we haven't considered. Like but in general, I think parametric tests catch a lot of the initial. Like if you literally just take the kernel, you put like all your inputs parametric, and you just make sure that you're not panicking, you're not having like some weird undefined behavior, and you like have some kind of sensible output.
Can you also have this optimization when you read multiple Parquet files, or is it only for one Parquet file?
No, so this is for multiple Parquet. Like you can also do this for multiple Parquet files. So, for example, for like Iceberg and Hive and whatever, and like if you just concatenate files, it would work as similarly on each individual file again, right? Yeah.
One question on the is-in operator that you also mentioned
Yeah.
in the end. Something that we do rather often is we have a table, let's say, full of items, and then we have another table with item IDs, and we want to sub-select this one table.
Yeah.
Usually the item IDs are also in a data frame, so what we would usually do, we would do a semi-join onto the table, but that's usually expensive.
Yeah.
So what we do sometimes is we convert that into a series, which is eager, and then feed it in is-in.
Yeah.
And the question would be, is that the best way to go about this? Is there some optimization that you could do on the semi-join that makes sense?
So at the moment, I think in Polars it is basically the best way to go around it at the moment. So that's basically what I mentioned here. So that's like what you can do is you can basically do this semi-join dynamically. So you first scan the small table, then you make that into a predicate for the big table, and then you do your semi-join like that. I think that is the best way to do it, but we don't really support that at the moment. But we want to support that, but just we haven't gotten around to it yet. Yeah, maybe one last question.
I was wondering if you could elaborate once more on the row group statistics, because I think I understood the problem that the code that you showed was the very simplistic code was too branchy and had vectorized.
Yeah.
But I don't think I quite got the solution. What is the solution? You ignore the row statistics and just look at the data, or how do you solve this?
So to make this into like some vectorized algorithm, that it's quite complex. But basically, there's filter algorithms that allow you to not have to deal with this branch being there, and that deal very well with indeed like low selectivity and high selectivity. So this is a very simplistic algorithm that works very well, but it's very slow because of several reasons. So what you basically want to do, like I didn't want to put it in the slides. I was thinking of putting it in the slides, but it's quite a big piece of code. That like you basically have to rewrite this to be completely vectorized. I think that's the answer. Okay, really last question.
Yeah. So when you have something that's like selects roundly like every other row or something, and you want to like load the other rows in, can you actually only decode only those rows that survive the filter, or do you like basically decode the whole thing and then apply the filter on top of that?
So for certain encodings, that's not like it's not possible to do it otherwise. But for the encodings where it is possible, we indeed we only decode we only load the data that is necessary.
So you basically load like the dictionary indexes only, and then apply the filter on those, and then only resolve them for you.
Yeah.
Nice.
Yeah. Okay. Well, thank you very much. And then